Good afternoon. I am Kim Do-yeon from the Security R&D team. I don't know if you remember me, but I have done a technical presentation online Dev Day last year, and I said I would like to have an opportunity to do another presentation in the next Dev Day. Dev Day has become Tech First, and so there is no Dev Day this year, but my dream has come true because I can do another presentation at Tech First. Last Dev Day, I have talked about identifying bugs in an effective way by using dynamic and static data flow in the smart contract for Ethereum, using Ethereum. And many people have taken interest in my presentation. And I also thought, how would it be to apply the CosmWasm smart contract, this technology to the CosmWasm smart contract? So now I would like to start my presentation on how to find bugs in CosmWasm smart contract. Before I go into the presentation, I will give you a brief introduction of myself. I am a second year liner and I am with the Line Security R&D team. I mainly focus on security R&D, and if there are good results, I do presentations in other conferences as well. Recently, I have done a presentation on Code Blue conference in Japan, and not only R&D but also do security consulting on various products within Line. My area of focus is software security, Fuzz testing, smart contract security, and I'm also very interested in identifying vulnerability automatically. So if you're interested in collaborating with me, please feel free to contact me. Next is the agenda of my presentation. In the introduction, I would like to talk about the background of the project, and I'll talk about how bugs are generated in CosmWasm. And then I'll talk about some of the obstacles that we have met during the project and what we have done to resolve these and how the project was designed. And then I will summarize. So, just to give you a brief background, blockchain is a type of distributed computing system. And the blockchain is very popular, and there are many different types of blockchain. For instance, there's Ethereum, Solana, Algorand, and Juno. And then there is the smart contract. Smart contract is a bundle of code and data that goes on top of blockchain. So it is a program that runs on blockchain. And then the smart contract is closely related to digital cash. So for instance, a contract on a single blockchain will exchange digital cash with other contracts, so various transactions can be made. Then how is Line related to blockchain? Line has a lot of blockchain related businesses. It has a coin exchange, it has Link, and also Line NFT. So depending on what type of blockchain you use, the type of smart contract will differ. Line uses smart contract based on CosmWasm, and it is generally created using Rust language. And I will call this CosmWasm smart contract. CosmWasm is blockchain within the Cosmos ecosystem. It is a smart contract platform. In other words, if Cosmos SDK is used, the blockchain can be made very simply. And all the blockchains made using Cosmos SDK is called Cosmos ecosystem. And if you want to make the smart contract supported within the blockchain, the CosmWasm can be used to create smart contracts. CosmWasm is run within the WebAssembly virtual machine. So when the CosmWasm smart contracts are compiled, it is converted to WebAssembly bytecode, and Ethereum smart contract is created using high-level language called Solidity, and after compiling, it can be run in the Ethereum virtual machine. It is converted into EVM bytecode. So CosmWasm smart contract and Ethereum smart contract run in different environments, and so their operation methods are completely different. Cosmos ecosystem is one of the most popular ecosystem out of all the systems that support smart contracts in the blockchain. This is the market cap for all the blockchains that support smart contracts as of October 31st. Cosmos was number 4. There is a gap between Ethereum, which is number 1, but if you look at the absolute market cap, it is still quite big. And as the technology is popular, it also becomes target of many hackers, especially because smart contracts deal with digital assets. If there are bugs in smart contract, it could lead to a great loss in assets. Ethereum, Solana, Juno has been attacked many times, and great amounts of money have been hacked. And what is surprising is that these hacking accidents are only a tip of the iceberg. So we can tell how important the security on smart contracts would be. So automatically detecting bugs within smart contract is a very hot topic among researchers. And one research is Smarty, and it's a tool. And I have done a presentation on this in the last dev day. Smartian, it uses dynamic and static analysis to find bugs in the Ethereum smart contract. It is a gray box concolic fuzzer, and through this paper we have identified that using data flow is very efficient in identifying bugs in the smart contract. So persistent stable variable value is tracked to look at the flow, and we can and this is a very important characteristic. So when the user sends the transaction, it is making a type of an external call. Generally, smart contract defines a certain series of functions and provides to the user, and the user calls these functions and sends the transactions to interact with the contract. And each function can read or write state variables, and these variables are the same concepts as the global variables. In other words, the variable's value is not volatile, and it continues even after the execution of the function. So if we call the f function, it will update the variable. And after we call the g function, we will use the updated variable value, and this value will be effectively used in storing the data of the smart contract. So for instance, if there is a smart contract that operates a bank, the balance of the customers to this bank will be stored in the variable of the contract, and the contract the contract functions will be called by the customers to withdraw or to deposit money. In the case of Ethereum, it is the number 1 blockchain that supports smart contracts. So it's been the number 1 target for hacking accidents. But not only Ethereum, but also other blockchains are widely used. However, if we search within Google Scholar, not many research results are found regarding CosmWasm related smart contract. And this is a search result from GitHub. If you search Ethereum smart contract security, you can get 161 repos. But if you do a search on CosmWasm smart contract security, you get 0 results. So people are using various different types of blockchains, but only people are only concentrating on Ethereum blockchain. So can you guess why I decided to move forward with this project? Many bugs have been found in the CosmWasm smart contract recently. In other words, the smart contract is not perfect. Therefore, before uploading the CosmWasm contract on the blockchain, it is very important to see if there are any bugs, because once the smart contract is uploaded on the blockchain, it cannot be corrected. But according to the search of GitHub, CosmWasm smart contract vulnerability cannot be found using a tool to find the bugs. So we wanted to create the tool to find bugs in the smart contract using CosmWasm, and we wanted to create an open source for it. But aren't you curious to find out what kind of bugs there are within the CosmWasm smart contract? We first need to research what kind of bugs are in certain programs. For the bugs that are found in the Ethereum smart contract, there are a lot of websites, but in the case of CosmWasm smart contract, it is very difficult to identify some of the bugs. So before introducing you to the testing tools, let me introduce to you the bugs that could be found within the CosmWasm smart contract. CosmWasm smart contract is written using Rust language. I'm sure you're familiar with the Rust language, but this language is very safe, and language-wise, it is very good at memory management. So compared to other bugs, the compared to other languages, it is very difficult to understand the bugs. So a lot of people use Solidity. Solidity is easy to is prone to get a lot of bugs. So the bugs in the Ethereum smart contract are difficult to identify in the CosmWasm smart contract. So in the SWC, which analyzes the vulnerability of the Ethereum smart contract, they have done a comparison with the CosmWasm smart contract. If we ignore the compiler warning, or if the program goes into panic, or if there are logical issues, CosmWasm smart contracts can create bugs as well. Well, due to time constraint, I won't be able to give you a list of all the bug types of CosmWasm within SWC, so I will jump into the impact. The old version, the modules with vulnerabilities, the functions that were used in there should not be used. Using vulnerable modules is dangerous, not only in CosmWasm smart contract, but in all programs. This example is a vulnerability that was found in CosmWasm. Many developers also always use lower cap for addresses. An address validate function will regulate correctly. However, the address validate function to call is address canonicalize, but if it is written in uppercase, then it will not be processed. And if there are many problems that become issues, the update is made. So we need to follow up these issues and update promptly. And also, if there is a certain address, and certain addresses cannot be accessed, I've maybe made it very complicated, but if there's a blacklist and whitelist, and if we were able to bypass these lists, what will happen? Users who are not supposed to have access to smart contract will access the smart contract, and it could lead to a lot of accidents. So in the Ethereum smart contract, many accidents like this have taken place. So for instance, if a certain user pretends to be the owner of the smart contract, that person could delete the smart contract and take all the money that were in the smart contract. CosmWasm smart contract, we don't know if such accidents have actually taken place, but there is a possibility to abuse the vulnerability in the block list, and the user can have access to smart contract. Now let me talk about the integer related bugs. The most famous integer related bug is integer overflow underflow. But the CosmWasm smart contract is written in Rust language, so the value does not change even during overflow or underflow, because as a default, the compiler level overflow and underflow is blocked. However, due to restorable error, the program can be stopped and panic can happen. Next is type conversion error. In the Rust language, conversion error does not happen that easily, but the compiler level issues can, because the compiler level issues can be blocked by type conversion. But if we were to force convert the 256-bit number to 126-bit, there can be an error and the program can be closed down. So how do we create a tool to find the bugs? I have found the bugs using fuzz testing or fuzzing. The tool to find the bugs using fuzzing is called fuzzer, and fuzzing repeats the actual execution of inputting random values, and it waits for errors to occur and crashing to occur. So the basic principle is very simple, but as fuzzing becomes more sophisticated, it is a very effective technology. So I first created a fuzzer using for the Ethereum smart contract, and I thought it would be easy to create a fuzzer for CosmWasm smart contract as well. But I bumped into a few issues when creating this. First, as far as I know, there are no known tools that find bugs for CosmWasm smart contract because there were no references. I had to learn how CosmWasm was operated.
And next, it was difficult to instrument the data flow for CosmWasm smart contract. Tracking data flow for state is important to bugs in smart contract, but there was no proper method. So we had to do black box fuzzing. In other words, we had to do fuzzing without instrumentation, just observing the outputs dependent on the inputs. How could we do this efficiently? Next, I'd like to talk about the illustration code, which has been modified from last year's Martian introduction. And we will look at the hints of how to find the bugs efficiently. State X, state Y, state Z. These state functions exist, and we have the functions. And we have a bug in foo. To trigger the bug, we have to have the right state Z value. But in order to change the state Z value, we need to change the value of state Y. But the function that updates the state Y value is setY function. And looking at it, in order to change the value of state Y, you need to change the value of state X. So in order to trigger the bug, you have to call the function in the following sequence. It looks easy enough to find out the sequence, but from the fuzzer's perspective, it's very difficult to find out that this sequence is meaningful because fuzzer just generates random input values. So of the random values, they don't know which can trigger the bug with a higher probability. So that is why we have to tell the fuzzer that this sequence has a high probability of triggering the bug through a certain mechanism. So when setX function is called, state X value changes thus, and when setY function is called, state Y value changes like this. Likewise, when foo function is called, state Z value changes. So the sequence of triggering the bug is created. And the 110 and the 300, these numbers are just arbitrary numbers because when you do fuzzing, you put in the random value so you can have other numbers as well. So up until now, we knew that the three sequences can change the state. And our purpose is to mark the sequence that changes the state so that we can try as much fuzzing as possible. Then we can find the right input value and get the probability up for triggering the bug. But As we saw from the state X, state Y, and state Z, we were able to identify them right away, but that's not really easy. So in order to find out the state values, we tried something, and I'd like to talk about that method. In this illustration, we're looking at the fuzzer structure for the CosmWasm smart contract. As the input value, there's the bytecode of smart contract, and there's the input from the schema. This is composed of two engines. One, schema, stores the information from the smart contract, and there are many types stored. So you need to implement the schema parsing that can do the parsing. After schema parsing is over, the schema information is sent to the fuzzing engine. As I mentioned before, fuzzing puts in random numbers and observes the program result values. So when a certain value is put in the program and when it's triggering the bug, then you store that value. Then you can recreate the bug in an easy way. Let's look at compile. When you're compiling the source code of smart contract, bytecode and schema are generated. For CosmWasm smart contract, it acts in the WebAssembly VM, so it converts to WebAssembly bytecode. When the smart contract is uploaded to the blockchain in bytecode, the source code information disappears. As you're well aware, bytecode is more difficult to read compared to source code. So unless you do reverse engineering, you cannot find out what it is. Then how can people find out what function is in the smart contract and how can they call that function? Schema file solves this problem. Schema file has the signatures of the known functions of the smart contract stored, and there's information about the type of the variables. So in the instantiate message, the messages related to instantiating the smart contract is stored in the instantiate field, and information about calling the function, the execute message, is stored in the execute message, and calling the information related to state is stored in the query field. Let me talk about schema parsing engine. When you call the function in the smart contract, it is called in the form of a transaction. To create the right transaction, you have to consider the adequate function name and variable type. So it's essential to parse the schema file. But in the schema file, because it has in storage which type of variable must be called together. And in order to do the type parsing, you have to consider the field called definitions also. And the type information is shown in the reference format. So what is defined in the definitions must be referenced. Of the types that are defined under definitions, you have to find out the other types in the definitions field so that you know exactly which type. Let's say you want to know the variable type called amount, then you have to look at what the coin type looks like. Coin is composed of two types, and the other amount field is unit 128. So to skim through the schema, you first store the information unit 128, you look at the coin, and then you look at the amount. In order to handle this, we use topological sort. It means that in a graph that is directional, there's no circulation. No circulation, in other words, everything is unidirectional. So this is very useful when you have to take care of tasks that has the order, because the order is fixed in type parsing, so you can be more effective in using topological sort. And then fuzzing engine. Basically, fuzzer is in a parallel mode, and as much as the CPUs, the workers are created, and in each worker, you have transaction sequence or seed is executed in the WASM VM. And each different worker has different contexts, and the contexts are only applied to that relevant worker. For example, in worker N, state X is put to 10, but from worker 1, because a certain function was called, state x is changed to 30. And in worker n, if you were to put in the value for state x, the value stays 10. So even if you change the state in seed 1, it does not affect the state of seed 2. If you find the bug in each worker, the result is stored in the shared memory, and then you execute, and you also store the information needed for fuzzing feedback. I talked about feedback earlier. Feedback is sort of a mechanism to make the fuzzing more efficient. So in order to indirectly find out the flow of state variable, we use the query message. Before and after one transaction, if you send the query message delivering the state value, then you know which state had changed. By executing that relevant transaction, you can store the information about a change in a certain state. For example, you send a query without any transactions to find out the initial state information, then you can find out the initialized state information. When you send the transaction, the state value may have changed. To find out the changed state information, you send the query again. So you find out the information gap, and then you know which state had changed. And you repeat that over the total seed. So if you do this, depending on the query message, you create a lot more load. And to solve this, you use parallelism. In the future, I think it will be another good research topic to how to efficiently handle the query message. I talked about the illustration code in the challenge section. And by sending the query message, you have the initialized state information. And when you execute setx 110, you send the query again, and you find out that the x value has changed. So the setx function knows it is known to change a certain state. You put that seed in fuzzing pool, and you execute setY, and you send another query again, and you find out that the y value has changed. Setx setY sequence is known to change the y value, and you put that in the fuzzing tool. And lastly, you execute setx sety setfoo, then the value of C has been updated. So you know that the sequence of setx, sety, setfoo is known to change the value of C, and you put that in the fuzzing pool. So the C that goes in the fuzzing pool is executed along with other variables. So as a result, 110, 300, if you put in these numbers, the bug is triggered, and then this transaction sequence is stored. If that is the case, how can our fuzzer catch what bug? I talked about the bugs. They cannot be all caught. For address bypass, you need deeper analysis. Simple execution does not find out which bugs are there. So basically, during the execution time, we detect the errors. In order to execute the smart contract, you need gas, but because there is a gas depletion due to lack of gas, and there could be panic, including assertion failure and integer overflow, and you could have out-of-bound error when accessing an array that exceeds its size. We can only detect runtime error, so we need further work on bug oracle. Then what can we do? As I mentioned before, we were only able to do black box fuzzing because we could not do instrumentation. If we do a precise analysis of the codes, I think instrumentation could be possible. So if you're interested in instrumentation, maybe you could take a look at CosmWasm itself. In our code, you should look at the executor part of the fuzzing engine. If you could do instrumentation, you could support the bug oracle that can find more bugs. So if you're interested in bug oracle, please look up the bug oracles part in the fuzzing engine. And then there are many types of messages that you can send when sending transaction. Right now, the following are supported: instantiate, execute, and query messages. If we could have further support, then it would be very nice. If you want to do work related to messages, you should look up executor and message in the fuzzing engine. In the message, you can decide how to compose the message, and in the executor, each type of message is sent to the smart contract. And I think it would be good to add static analysis if it is possible. In relation to static analysis, there's been no engine separately made for that. So I think it would be good to have that engine run before fuzzing. And there could be many features added to make a better tool. We are going to make this fuzzer open source. So if you're interested, please come and take a look at our tool. I think it would be wonderful to co-develop. So this is my contact information. I would like to thank you very much for your attention.
Thank you very much. We're now going to begin the Plus Talk. We are going to receive questions and answer those questions. Those of you who have questions, please press the question mark and send in your questions. Mr. So Hong-sop of Linux is going to preside this session. Can you please introduce yourself, Mr. So? Hello, I am the lead of Line blockchain development. My name is So Hong-sop. Thank you for making the fuzzer for CosmWasm smart contract, and thank you for the presentation. I hope you take this time to have a drink some water and take a rest. Fuzzer presentation from last year, I was very impressed, and I thought CosmWasm Fuzzer would be so useful. And thank you for developing that. And as the developer of the blockchain main lab, I was very happy, and the CosmWasm user and the developers would be very happy to see this, because analyzing black box fuzzing is quite limited. So using the RUT language when this is deployed in the chain, and I think WASM will allow us to do some analysis. So analyzing WASM and analyzing Fuzz, what do you think about this idea? Well, as you have mentioned, WASM bytecode analysis, I thought would lead to better development of a better fuzzer. So for what's next, I have talked about the stacking analysis, and I talked about the development of stacking analysis. So stacking analysis. So if I could add stacking analysis, the bytecode would be analyzed in more detail, and I think it could help the fuzzer.
Thank you very much. So I think it would be wonderful to analyze WASM. So you're just doing black box fuzzing, so it must have limitations. Overall, there could be Rust language solving the issues, but in your presentation, you talked about executing TX, and you're doing bug analysis, and you're able to identify the bugs. But the query portion, if that has bugs, then how can you detect those bugs in the query? Well, actually, that is a very good question. Right now, in the fuzzer, they look at the query message value, and as was mentioned, if the query message itself has an error, then within that message, there's no information to be gained. So in that case, it's very difficult to provide accurate feedback. But in the query message, generally speaking, compared to execute message, they're simpler. So in developing, the query message is used to try to acquire information. So that was the basic assumption. Thank you very much. But query is bug free, so maybe we could have additional development to work on that. And as I mentioned earlier, the Rust language compared to Solidity is more stable and can solve many issues. Solidity, EVM, I think Rust is better. So personally, I think Rust is a very good language. But in mainnet or in developing smart contract, there could be potential issues. You did mention them. But in development, is there anything that you need to watch out for? In developing, what are some of the precautions that we need to take? For example, it's about Cosmos blockchain and also goes for other blockchains. In the smart contracts, we could have this type of bug that occurs, transaction order dependency. So the sequence of transaction, how depending on how that is committed, the smart contract execute results could be different. So this type of bug in the smart contract is stored the values like block hash information, and they're dependent on these values. So if you develop this, these values could be manipulated. So we should not be over dependent on these values that are easy to manipulate.
Yes, so in developing smart contract, we have to use only the information that we have. And I think that's the most difficult problem. And that is why the Oracle issues appear as well. So when fuzzer is used, I'm sure you've done a lot of tests. So EIC 20 or EIC 71, EIC 20 or EIC 71 functions. So if a smart contract has those functions, how much system do you need and how much time do you need? Well, frankly speaking, I have not been able to measure them accurately, but as far as I know, EIC 20 smart contract, the number of functions would be about 10. So if we look at the fuzzers for now, the ones with only 10 functions, there's no problem operating that. And the number of transactions as they increase, of course, the performance will be uh, lowered, but we can deal with those using parallelism. So I think we can develop in that way. Thank you. I am very eager to use it. And the black box fuzzing, when we use black box fuzzing, the parameters, reading the schema, and then putting in the parameters randomly, and you said you look at the results of that. But I think there is the order of the functions. Do the orders are the orders tested randomly, or the developer or auditor creates a scenario to run the test? How is it done? Well, this fuzzer is basically you can automate it. So when you call the function, of course, the order is assigned randomly. But as you know, all functions, the order of the functions, if they are all random, we will not know which functions can, well, we will be able to see which functions, well, we won't be able to see which functions can identify some of the meaningful bugs. So we get the feedback and which function sequence can change the state, we can mark that, and the sequence of that function, we can concentrate on the fuzzing of that sequence of the function. So if it's a bug that appears frequently, you will mark it. Okay, I understand. So, but what if the bug is detected, and when you analyze the bugs, I've assumed that it's not easy. Is there a know-how, or is there a better way to do it? Well, know-how. Frankly speaking, the rather than general binary, smart contracts are smaller in size. So smart contracts, when you analyze the smart contracts, you can see, you can detect the bugs more easily, relatively speaking. So yes.